Ionization constant of weak acids. When we talk about ionization constant, obviously the reaction will happen in the water. So suppose this is the weak acid. It can be, for example, CH3COOH. So this hydrogen is this part and X is this part. Okay. So it means if I consider this one, this X minus will be CH3COO minus. So in general case, I am talking about how we will deal with it, how we will solve these type of problems. We will first consider what is the initial concentration of all reactants and products. So initial concentration, I will say C. Okay. Then I will talk about how much got dissociated, means how much got used up. So till now you have done that if X got used up here and it is the ratio 1 is to 1 is to 1. So X will be produced and X will be produced. Here slightly we will change the concept. However, it is same thing, right? It is same thing. We will write it differently. Instead of saying X, I will say how much part of it got dissociated. So suppose I have 1 mole, okay, of this weak acid and say 1/4 part got dissociated. Then if I will have 2 moles, then 2 into 1/4 part will get dissociated. If I have 3 moles of this weak acid, 3 times 1/4 part will get dissociated. Okay. So what we are doing actually, we are multiplying this 1, 2, 3 by the dissociated part. So here what we are writing here, this is C, this is C, 1, 2, 3. Okay. See, this is degree of dissociation, means how much part got dissociated. If it is, we are talking about unit moles, okay, unit concentration, then how much part will get dissociated. This is known as degree of dissociation and it is written as alpha. So it means this whole part which will get dissociated, which is actually X, is C alpha now. So if I have 1 mole, only alpha will get dissociated. If I have 2 moles, 2 alpha. If I have 3 moles, 3 alpha. If I have C moles, then C alpha will get consumed, will get dissociated. So here the change will be minus C alpha. Why minus? Because it is getting consumed. And because the ratio is 1 is to 1 is to 1, it means same moles will be produced. Okay, 1 is to 1 is to 1. Same number of moles will be produced. Here X is C alpha. In simple terms, what we used earlier as X is C alpha here. So at equilibrium, what will be the concentration? It will be initial concentration and then whatever got consumed, that is C minus C alpha. Okay. C alpha here, total here C alpha, total here C alpha. And now we can use equilibrium concentrations to get the equilibrium constant. Equilibrium constant is here ionization constant. Here it is called ionization constant of this weak acid. Otherwise, in general, it is equilibrium constant. So it will be products concentration raised to their stoichiometric coefficient. Stoichiometric coefficients are 1 here. Okay. Here also it is 1. Remember, pure liquids will not be considered. So water is pure liquid. We will not consider its concentration. Then divided by reactants concentration, that is weak acid concentration raised to its stoichiometric coefficient, which is 1 here. Okay. So we are talking about monobasic acids. What are monobasic acids? Monobasic acids are those ones which give you 1 mole. If 1 mole is dissociated, you will get 1 mole of hydrogen ions. Those are called monobasic. Why basic? Because this 1 mole of hydrogen ion will neutralize 1 mole of base. 1 mole of base will be neutralized. That's why it is known as monobasic acid. Now coming back to the equilibrium constant, if we simplify it, we will get C square alpha square divided by C. Take C common from here. And then 1 C will get cancelled. We get C alpha square divided by 1 minus alpha. So in terms of alpha, that is degree of dissociation. the ionization constant of acid can be written. You can use formula directly. In numericals, if it is monobasic acid, then you can use this formula directly. Ka is called dissociation or ionization constant because dissociation is taking place. You can call it dissociation constant, you can call it ionization constant because ions are produced, and it is equilibrium constant simply. In terms of molar concentrations, if we talk about molar concentration, this Ka will be simply products concentration raised to their stoichiometric coefficient divided by reactants concentration raised to their stoichiometric coefficient. At a given temperature, Ka will remain constant. Okay. So this gives us the measure of the strength of the acid, how much strong the acid is, how much weak the acid is. So larger the value of Ka, the stronger is the acid. This is something you should remember. You can use it to determine the order of the acids in terms of their strength. So increasing order of acidic strength, decreasing order of acidic strength, you will use Ka here. Ka is a dimensionless quantity, you should remember, with the understanding that the standard state concentration of all species is 1m. So normally we will be doing calculations in standard state. In a standard state, we consider the concentration as 1 molar. In that case, Ka will be considered as dimension quantity. pKa, as we know that I told you that pH is equal to minus log H ion concentration. Okay. In general, for anything, you can write Px equals to minus log x, right? This is what you can do here. Okay. In general. So that's why pKa will be minus log Ka. Now the question. The ionization constant of HF is 3.2 into 10 power minus 4. Ionization constant. What is ionization constant? Ka. Ka is ionization constant which is given. Calculate the degree of dissociation. What is degree of dissociation? Alpha. Alpha is asked. Ka is given 3.2 into 10 to the power minus 4. So remember, in exam you will write like this. Given Ka, alpha is asked, and HF in its 0.02 m solution means the molarity, initial concentration of this acid C is given. C is 0.02 moles per liter. Calculate the concentration of all species present, that is S3O plus hydronium ion. Why hydronium ion will be there? It will be from this HF and it will be from water dissociation also. Then F minus will be from this HF dissociation only. HF, obviously some part will not get dissociated because we have Ka 3.2 into 10 power minus 4. It means not much dissociation will take place in this case. So some part of HF will be there. So if I consider with the reaction, there are possibilities, two possibilities. HF will get dissociated in water, will give you hydronium ion and fluoride ion, and obviously water will get dissociated, it will give you hydronium ion and hydroxyl ion. Remember, Ka is given for this HF, and for HF we will have Ka concentrations only hydronium ion, fluoride ion and HF. Obviously this is pure water, will not be considered, and you will not consider concentration of OH minus also for Ka, because Ka is related to only HF and this reaction does not have OH minus. Okay. So how to solve it? Now if you see the values here, Ka is of the order of 10 to the power minus 4 and Kw is of the order of 10 to the power minus 14. So as compared to Ka, there is hardly any dissociation taking place in case of water. So you can neglect the hydronium ion concentration produced by water itself. Okay, it will be negligible. So you will compare the equilibrium constants of the two reactions. and you will decide whether you can neglect the concentration of hydronium ion from one reaction or not. Otherwise, if it cannot be neglected, suppose this is 10 power minus 4 and this one is of the order of 10 power minus 6, you will not neglect it in that case. So the difference should be more than 10 power minus 3, means the difference should be more than or equal to or greater than 10 power minus 4. Then you can neglect it, or then you should neglect it. So as Ka is much greater than Kw, obviously the hydronium ion concentration we will consider only because of Ka, not Kw. We will consider only one reaction. Here we will say initial concentration, it is given C.02 here, and obviously here we have 0. Then it will be minus C alpha. If you remember, this will be C alpha, this will be C alpha, if you remember, right? So we have written it like this: minus C alpha plus C alpha plus C alpha. So at equilibrium, obviously it will be C minus C alpha. This will be C alpha. This will be C alpha. This is just for explanation. In exam, if this question appears, because this is monobasic acid and you have to consider only this one, okay, you can write Ka as simply C alpha square divided by 1 minus alpha. You can use this formula directly. I have explained it just to make you understand why we are doing it. From here you will get Ka as 3.2 into 10 power minus 4, which is given. This is actually given, 3.2 into 10 power minus 4. Alpha has to be calculated. So from here now you will simplify this to get quadratic equation. From here you will get alpha equals to plus 0.12. You can apply the formula that roots alpha will be equal to minus b plus minus square root b square minus 4ac divided by 2a. Quadratic equation, how do you solve that? And you will neglect the negative value. You will consider only the positive value because dissociation cannot be negative. Once you got alpha, you can calculate the concentration which is asked. I'm going back to the question, okay? In question, you have been asked to calculate the composition, okay? Species present, calculate the concentration. Concentration means composition of hydronium ion, fluoride ion, and HF. What is this concentration? If you see this particular value at equilibrium, this is the concentration at equilibrium. So at equilibrium, if you get the value of alpha, just substitute the value of alpha here, you will get hydronium ion concentration, and same is fluoride ion concentration. Substitute the value of alpha here, you will get HF concentration. So that's what I am doing here. I've got alpha, I will calculate hydronium ion concentration as C alpha, same will be fluoride ion concentration, and HF concentration will be C minus C alpha, this one. Substitute the value. That is what is asked, concentration of hydronium ion, fluoride ion, and hydrogen fluoride. Now the pH. pH is minus log H ion concentration. Substitute the value. Remember, you will be given the value of logs or you will be given log and anti-log tables. So you should learn to take log using log and anti-log tables as well. If your teacher says that they will be providing logarithmic, anti-logarithmic tables in the exam. So just I'm going back to show you the question again. Try to recall how we solved it. Here you have been asked to calculate the concentration of these species and pH. For pH, obviously you know you need hydronium ion concentration, which obviously you have been asked to calculate. How do you get these concentrations? For monobasic acid, HF plus H2O will give you hydronium ion concentration plus fluoride ion concentration, and we will consider only this reaction. We will not consider dissociation of water because dissociation of water is equilibrium constant is much less than the equilibrium constant given here. So for this, we will say Ka will be C alpha square divided by 1 minus alpha, and this Ka is given, we substituted that value. The C is given 0.02, substituted that value, we got alpha. Quadratic equation we solved 0.12, and then we substituted that value here. This will be C alpha, this will be C alpha, HF will be C1 minus alpha at equilibrium. So you should remember, for monobasic acid we will be using it again and again. For monobasic acid, equilibrium concentration of acid will be C1 minus alpha, hydronium ion will be C alpha, and anion concentration will also be C alpha. In case where we have neglected the dissociation of water, means the hydronium ion due to water, in that case, this is the case. Okay. Otherwise, if you have to calculate the fluoride ion concentration, hydronium ion concentration, you will have to calculate from both. That is hydronium ion concentration C alpha from here and from water as well. That will be the final hydronium ion concentration, and that will give you final pH. So that once you got hydronium ion concentration, you will say minus log hydronium ion concentration to pH. It is important that you understand where to ignore the reaction, any one reaction, mostly the dissociation of water providing the hydronium ion. But this is not hard and fast rule that it will be only water. There can be any two reactions given. The one where there is hardly any dissociation as compared to the other one, you will neglect. Next question. The pH of 0.1 m monobasic acid, if it is monobasic acid, you know only 1 mole of hydronium ions will be produced, 1 mole of hydronium ion, okay, is 4.50. Calculate hydrogen ion concentration and anion concentration and HA concentration at equilibrium. Also determine Ka, pKa of the monobasic acid. So this is the reaction you will use. I have used simplest form. Otherwise, if you want, you can write Ha plus H2O gives you H3O ion concentration and A minus. Same thing. The reason is because pure liquid you will not consider H2O, and hydronium ion concentration is same as hydrogen ion concentration. So both the reactions are actually same. Initially you have 0.1 mole and here it is 0, here it is 0. Then some dissociation will take place. Suppose X got dissociated. Remember, here I am not using the formula C alpha square divided by 1 minus alpha. You can do this question by using that method also. Okay. Why I am not using it? Because the degree of dissociation has not been asked. The degree of dissociation has not been asked. Alpha has not been asked. So there is no need to unnecessarily do the complex calculations. So means at equilibrium I have 0.1 minus x and x concentration. Okay, means minus x got consumed, x got produced, x got produced. So pH will be minus log H ion concentration. Okay. Therefore, H ion concentration will be anti-log of pH. Right? pH is given. pH is given. From here I can get H ion concentration. H ion concentration will be from here anti-log of pH. And this value will be either given in your exam or you will be provided anti-logarithmic tables. H ion concentration and anion concentration same, both are X. Okay. So the moment you got H ion concentration, same will be the anion concentration. So you got H ion concentration and anion concentration. Now you have to calculate HA concentration because you know the value of X. This is the value of X because this is H ion concentration. It is X. Substitute this value here. You will get the concentration of the acid also at equilibrium. Because X is of the order of 10 power minus 5, if you subtract it from 0.1, there will hardly be any change. So it will be approximately 0.1. There will hardly be any change. Thus Ka has been asked. Ka will be the products concentration raised to their stoichiometric coefficient divided by reactants concentration raised to their stoichiometric coefficient, and we know all these values, we have calculated. So substitute these values, get the value of Ka. Once you have Ka, you know pKa will be equal to minus log Ka. Substitute this value, pKa equals to minus log Ka, that is 8. This question can appear in 2 marks, can appear in 3 marks as well. Okay, but it's not tough, very easy one. Next question. Calculate the pH of 0.08 m solution of hypochlorous acid HOCl. Ka of the acid is 2.5 into 10 power minus 5. Find the percent dissociation of HOCl also. Okay, percent dissociation. Now, percent dissociation means you have to calculate alpha in percent. Okay, percentage of alpha. That's it. You just calculate alpha, multiply that by 100, you will get percentage dissociation. pH is to be calculated. C is given, Ka is given. Question becomes easy. Solution will be HOCl will get dissociated with water and will give you hydronium ion concentration and hypochlorous. Okay. So initially concentration is given, you have 0.08 and no product, then at equilibrium it will be 0.08 minus x, x and x. Now here in this question, it is possible to use C alpha, C alpha, C alpha also, because from there you will directly get the degree of dissociation, multiply that by 100, you will get percentage dissociation. I will tell you how to get percentage dissociation if you use x. Okay, if you use x, then also you can calculate the percentage dissociation, means how much got dissociated means x divided by how much you had. Okay, you had 0.08. Okay. So Ka here will be given by products concentration divided by reactants concentration raised to their stoichiometric coefficient using these values at equilibrium. Substitute these values. Okay. And Ka is already given. This Ka is given. Substitute this value also. So from here, if you see Ka is of the order of 10 power minus 5, and if it is of the order of 10 power minus 4 or less, you can neglect the x here in the denominator. Remember, you cannot neglect x here, because anything may not be negligible if you compare it to itself. Okay, it is 100% of itself, so you can't neglect it. But if you consider this x as compared to 0.08, then it can be neglected because there is hardly any dissociation. So instead of 0.08 minus x, you can write 0.08 only. So this part is important. You should remember 0.08 minus x in this case will be approximately equal to 0.08. In general, if Ka, and in cases of base, when we will be talking about, it will be Kb, okay, is of the order of 10 to the power minus 5 or less, then C minus C alpha, that is C 1 minus alpha. Remember, this is C minus C alpha. Okay, it is actually C, and x is also C alpha. C is 0.08 here in this case, will be approximately equal to C. Why? Because 1 minus alpha will be approximately 1. Alpha is negligible. The dissociation will be negligible. Degree, the part which gets dissociated is negligible. So as compared to 1, the part of 1 which is dissociated is negligible. So this is 1. C into 1 will give you C. So write it somewhere. If you want to memorize it, memorize it. If you have understood it, very good. So if Ka, Kb, equilibrium constant in general is 10 to the power minus 5 or less, then C1 minus alpha will be C, or 1 minus alpha or 1 minus alpha will be just 1. 1 minus alpha will be 1. C 1 minus alpha will be C, 1 minus alpha will be 1. Now simplify this one. If you simplify, you get X as 1.41 into 10 to the power minus 3. And X is hydrogen ion concentration or hydronium ion concentration in this case. Now come back to the question what is asked. Calculate pH. Once we get H ion concentration, substitute in the formula pH equals to minus log H ion concentration, you got pH. So first part done, pH obtained. Now to get the percentage dissociation, what we can do, percentage dissociation can be how much got dissociated divided by initial concentration. So we can say how much got dissociated divided by initial concentration. This will give you fraction which got dissociated, fraction. When you multiply it by 100, it means percentage dissociation. Substitute the values. How much it got dissociated is X. X got dissociated. Okay, X got dissociated. How much initial value was there? 0.08. X divided by 0.08 and X is 1.41 into 10 power minus 3. So when we substitute the value, how much it got dissociated divided by initial concentration into 100, you will get percentage dissociation 1.76%. Now you can get the same answer by C alpha. Also X equals to C alpha. So remember here it is X divided by 0.08. That is 1.41 into 10 power minus 3 divided by 0.08. How I can get the same answer with the degree of dissociation also, because this X is actually C alpha. This is C alpha. This X is C alpha. So everywhere X is C alpha. So once I got this value, that is C alpha, okay, C alpha value, I can get alpha from here and I can multiply that alpha by 100. I will get percentage dissociation. If I multiply, if I write here C alpha here, okay, so C alpha is X, it means it will be 1.41 into 10 power minus 3. From here, alpha will be 1.41 into 10 to the power minus 3 divided by C. And what is C? C is 0.08. If I need percentage, I need to multiply it by 100. So I get the same thing. 1.41 into 10 power minus 3 divided by 0.08 into 100, which I got using the percentage dissociation by the formula dissociation divided by initial value into 100. That is 1.76%. Same thing I will get using another method also, 1.76%.